In this lecture, we are going to describe Boolean sequential circuits, at least some of them. The circuits that we have seen so far fall under the category of combinatorial Boolean circuits, and in such circuits, the output or outputs depend on the combination of inputs, but not on the sequence in which the inputs were given. In other words, the output depends on the present values which the inputs have. As a result, the output is always a function of the inputs. And that is exactly what combinatorial circuits are actually used for. They implement Boolean functions. On the other hand, the output of the other class of circuits, the one we are going to talk about today and in the next lecture, depend on not only what the input is at present, but also on the history of the inputs, the order or sequence in which the inputs were given. That is why they are called Boolean sequential circuits. And one very important use of sequential circuits is in a computer memory, in remembering what kind of inputs were actually given in the past. Now, the simplest kind of memory circuits that we have are called flip-flops, rather irreverently. Well, they have a more official sounding name, bistable multivibrators, but flip-flops are what everybody calls them anyway. We will begin our discussion of Boolean sequential circuits with a description of flip-flops made out of NOR gates or Nand gates. As the alternative name, bistable multivibrator suggests, a flip-flop is a device with two distinct stable states. Now, because the states are stable, a flip-flop remains in one of these two states until triggered by external impulse to the other state. And once it goes to the other state, usually it stays there. That's exactly what bistable means. And the state in which the flip-flop is remembers what input was given in the past. That is why flip-flops form the basic building block of computer memories. So let us take a look at a simplest kind of flip-flop circuit, something which also goes under the name of Rs Latch. Here Rs stands for reset and set. And here we have two implementations of the Rs Latch on your screen right now. The one on the left uses NOR gates only, the one on the right uses Nand gates. Let me first explain to you how a NOR gate implementation of the latch, the NOR latch, works. As you can see, the Rs NOR latch is composed of two NOR gates with two inputs marked R and S, reset and set, and two outputs which have been denoted Q and Q bar. From the notation itself, it seems that the two outputs are complements of each other. As we will see, that is almost always right, at least under situations where the latch is working properly. But before we get into when a latch works properly and when it does not, let us first try to understand what this circuit is supposed to do. In order to understand the mode of operation of this NOR-based Rs latch, let us first recall a few important properties of a NOR gate. Remember, the NOR gate produces an output Y given inputs A and B, which is given by A or B knotted. That is A naught and B naught. Now, one immediate consequence of this is the following. If one of the two inputs, let's say B, is high, then Y is low. So B being high, in fact any one of the two inputs being high, forces the output to be low. On the other hand, if a given input B is low, then of course B bar is high, Y is simply A bar, the complement of the other input. Now based on these 2 points, let us try to understand how the NOR latch works. We will begin with the input combination 0 and 1. R is 0, S is 1. Remember, S is called the set input. So this is essentially an attempt to set the Rs latch. Now notice that since S is high, that immediately makes the output of the lower NOR gate low. That is, Q bar definitely is low. This Q bar is of course fed back to the input of the upper NOR gate. Now what happens is that the upper NOR gate has 2 inputs, both of which are low. R is low because that's what the input was, and the other input is low simply because it's being fed back from Q bar, which has been driven to a low value because S is high. And that of course produces an output for the upper NOR gate which is high. So the output in this situation is Q bar is low and Q is high. And note, Q is also fed back to the lower NOR gate, but frankly the value of Q does not really matter in this case because S being high, Q bar goes low anyway. And this is the condition which we call the set condition. The latch has been set. Q has been set to high. That's what set means. Now what happens if after you do this, the input S returns to what its natural value is? In this case, the natural value for both inputs are actually 0. Let's ask ourselves what happens when S returns to 0 once the output has been set by S going to 1. Now the situation is the 2 inputs are both 0. Now if an input is low, the output is completely determined by the complement of the other input. Notice that in this case the other input actually comes from the 2 outputs. Right now we are examining a situation where the Nand, where the NOR latch has been set, that is, we have Q equals 1, Q bar equals 0. But note that Q equal to 1 will come back here as the input to the lower NOR gate, and because you have 0 and 1, one of the 2 inputs is 1, the output will go to 0. So the output 0, which was the original state of Q bar, stays as it is. On the other hand, this 0, when it goes back, ensures that both inputs of the upper NOR gate are 0, and hence the output has to be 1. In other words, whatever the Q and Q bar values were before, they stay unchanged. Now at this stage I am not writing down 1 and 0 for Q and Q bar, for the simple reason that we will find that the basic property here, when the input R and S are both 0, is that the output simply does not change. It retains its value from what it was before. To see that, let us consider the other possible input combination where R is 1, S is 0. This is the so-called reset combination. And that exactly is why the input is labeled R for reset. Now, it's very easy to see that under this situation, all that happens is that the role of the upper and the lower NOR gates just reverses. And as a result, what we end up with is the following. Since R is high, Q definitely goes to low. And now this Q comes back here, ensures that both inputs of the lower NOR gate are low, and therefore the output of the lower NOT gate is 1. So this is where the latch is reset. Q is sent back to 0. Q bar goes to 1. Note that when you have the 0-1 combination of the inputs R and S, the latch is set. Q is set to 1, Q bar is set to 0, irrespective of what the situation was before. When R is 1, S is 0 on the other hand, Q goes to 0, Q bar goes to 1, the latch is reset, and this happens irrespective of what the state was before. But what happens if we go back to 0, 0, the natural state of the inputs, after we have reset the latch? Note that now you have 0 and 0 as the two inputs from R and S, but the other two inputs are one up here from the output Q bar, and this one is 0, which has been fed back from the output Q. And note that if you have 0, 1 as one input to the NOR gate, the output has to be 0, and 0, 0 gives you an output of 1, which again means that the 0 and 1 values for Q and Q bar respectively are stable. They are not changing. So basically what happens to the output here is that the output does not change. NC here stands for no change. The output just stays what it was before. And so this is what we call the memory state. And note that here the output does not depend on the precise combination of inputs. Both inputs are 0 and 0 in both the cases. However, in one case the output is 1 and 0 because the latch had been set before that. In the other case, which is if you return to 0, 0 input after you reset the latch, that is put R equal to 1, S equal to 0, Q stays 0, Q bar stays 1. The output does not depend on the present values of the input but on the past behavior of the inputs. That, of course, is what a sequential circuit is supposed to do. Let us now come to the last of the 4 possible input combinations, the one which I have not mentioned so far. What happens if R and S are both set to 1? Now this condition is called race, and if you look at a standard textbook, you will find that the outputs are not even marked in this case. In most textbooks, they are just labeled with a star, implying that there is something crazy going on here. Frankly, if you think of the basic theory of NOR gates, it would be rather difficult to see what's so crazy about this situation. After all, a NOR gate always gives you a low output when one of its inputs is high. So, of course, what really happens if both inputs R and S go high is that Q and Q bar both go low. Now, this is the case where the nomenclature Q and Q bar fails. As we had said a while ago, Q and Q bar seems to imply that Q bar is the complement of Q, and that works in almost all the cases. Actually, it works for the 3 cases that we have discussed before this. However, in this case, Q is not the complement of Q bar. In fact, both of them are the same, namely 0. As we have also said, this is the condition where the latch is not really working properly, or rather, this is the condition where we don't want our latch to go at all. This is what we would want to avoid. Why don't we want this? The answer is in the label race that we have put on this particular input combination. To understand what that means, let us take a look at what happens when you start with this situation. R and S are both high, and hence Q and Q bar are both low. And then allow the latch to go back to its natural input situation. Remember, the natural input state for both the inputs is actually 0. So, after a while, both R and S return to 0. But now you have a problem. Notice that the outputs which were 0 and 0 both are feeding back to the inputs of both the NOR gates. And that seems to imply that the output of both NOR gates would go to 1. However, that is not possible, because if for some reason Q goes to 1 before Q bar goes to 1, then the input to the lower NOR gate would become 0 from S and 1 from the Q feeding back, and hence the output will stay 0. As a result, what you will get is Q equal to 1, Q bar equal to 0. But that is presupposing that the output of the upper NOR gate changes first. If the output of the lower NOR gate changed first to 1, then what would happen is that it would force the output of the upper NOR gate, namely Q, to go to 0. So now it's a race between the two possibilities. Once you set your inputs to 1 and 1, R and S to both 1, the outputs Q and Q bar are well defined. They have to be 0. But the problem occurs when the inputs go back to their natural state of 0. And once that happens, whether you will get Q equal to 1, Q bar equal to 0, or Q equal to 0, Q bar equal to 1, simply depends on which one of the outputs changed first. That could be either because of the fact that the two inputs R and S did not go back to 0 simultaneously, or it could be due to the fact that one of the two NOR gates is faster than the other. That would invariably be the case actually. You cannot have identical responses for two different NOR gates. So what you would end up with is a situation where in the natural state of the inputs 0 and 0, you cannot really be sure what the output is going to be. The output will depend on whichever thing goes first. That is what race means here. Let me stress once again, when the inputs are both 1, that is not really the race condition. You label that with race, but the race actually occurs when the inputs go back to 0 and 0. And this is the situation you would want to avoid, where you cannot predict what the output will be. The output will actually depend on chance factors like which of the gates is faster and so on. So if you were using an Rs NOR latch, you would try to avoid this situation where inputs are both 1 at the same time. In fact, many of the modifications of this NOR latch that we actually use are designed in order to avoid the possibility of the two inputs going 1 at the same time. As we have already mentioned before, the other kind of latch that you could have would be implemented using NAND gates only. Here also you have two inputs marked R and S, reset and set, and the outputs of the NAND gates in this case are fed back to one of the inputs. The operation of this NAND-based latch works almost along similar lines to the NOR-based latch, the only difference being in the fact that here the memory state is actually where R and S are both 1. Remember that when one input to a NAND gate is high, the output depends only exclusively on the other input. In fact, the output is the complement of the other input. So when R and S are both high and Q and Q bar are complements of each other, they are fed back to the other NAND gates and they stabilize or maintain whatever output you already had. It should be pretty easy for you to figure out that if you have 0 and 1 for R and S, Q would go to 1, and that of course is set. After that, if the inputs relax back to their natural state, which in this case are both 1, you are going to maintain the Q equal to 1, Q bar equal to 0 scenario. On the other hand, if I reset the NAND latch first by making R equal to 1, S equal to 0, and then both inputs went high, then Q would stay 0, Q bar would stay 1. In this case, the race condition occurs when both inputs are low. Once again, the output has been marked with an asterisk. But that does not mean that you do not know what Q and Q bar are when R and S are both 0. In fact, when R and S are both 0, it's easy to see that Q and Q bar will be both 1. This is the case that you would want to avoid simply because once again when the inputs went back to their resting or natural state, which is both 1s, then the output cannot stay 1, 1, has to change to 1, 0 or 0, 1, but which one actually occurs depends on which of the two NAND gates is faster or which of the two inputs R and S went to 1 earlier. So let me stress once again that this is the situation that you would want to avoid. And of course you would want to design more advanced latches where this race condition would not occur. Let us now look at one particular application of this Rs latch. What we are considering here is a circuit, well actually it's more of an application called the switch debouncer application. To understand what that is, just remember that whenever we have a switch which we throw from the on state to the off state or from one end to another, there is a chance of the switch bouncing. That is, the contact may not be made right properly. It may just jump back and forth a bit, and typically that's what happens every time a switch is thrown. You do make contact in the long run, but before that contact is made, there are several times when the thing can go on and off over a very, very short period of time. Now that kind of thing happening in a digital circuit might completely throw the circuit off from what it is supposed to do. The debouncer essentially avoids that problem. Note that here we are using a NAND based latch, and the two inputs to this NAND based latch, the R and the S, have been labeled start and clear. And it's our job basically to ensure that when we switch our key on the left of the diagram to clear, the output marked CLR for clear, that goes high, CLR bar goes low and stays there. Now, before we proceed any further, I must introduce one more important point here. Notice that one of the two junctions of the switch, the one marked start or the one marked clear, is going to be grounded, but the other one is not grounded, neither is it connected to a high voltage. So that's a floating voltage. Now, what happens when the input to a gate is floating? That depends strongly on how the gate is constructed. So different kinds of gates with different kinds of internal construction may behave differently for a floating input. Now, one of the most common kinds of gates that we have use what is called TTL, transistor logic. We are not going to go into the details of that in this class simply because we don't have the time to do that. But one important point about TTL logic is this. If an input is floating in a gate which works on the basis of TTL logic, then that input essentially is high. So floating means high. This is what you have to remember. So what has been drawn here on the circuit is that the start junction is connected to the ground. That definitely is low. And the clear is floating, so that's high. So what you have are 0 and 1 as the output. And the 0 input to the NAND gate, the upper NAND gate, drives CLR bar to high. And now both CLR bar, which has been fed back to the input of the lower NAND gate, and this input marked clear are both high. CLR bar is high because the output is high, and clear is high, of course, because it's floating. So CLR is clearly low. So that's what happens at the beginning, the CLR output is low, CLR bar output is high. Now what will happen if we were to throw the switch from start to clear? Notice that is exactly what is being shown here. Initially start is low, clear is high. And at this point of time, this is of course a time diagram, time is flowing to the right. And at this point in time, the key is thrown. The moment the key is thrown, the start junction becomes floating, so it goes high. And the moment the key makes contact with the clear junction goes low. So of course, when that happens, it's easy to see that CLR will go high and clear bar will go low. However, that is not the end of the story. What might very well happen is that you might have bounces, that is, the switch may not connect to this clear cleanly. It may connect, then get disconnected, then connect again, and so on. So clear essentially goes low because it's connected to the ground, but then goes high again because it's floating, then go low again several times. Now, if we were to feed this clear signal directly to a digital circuit that we are trying to control with it, this kind of going up and down would completely destroy the intended result that we would want to have. But notice what is happening once we feed this whole thing through this Nand latch. Now, once the start has gone to high and clear has gone to low, the output CLR, that of course goes to high and CLR bar goes to low. But then when the switch bounces, note that both start and clear are high, but when both start and clear are high for a NAND latch, both R and S inputs are high, that is the memory state. So the CLR output does not return back to 0, it actually stays where it is. So right through this bouncing of the clear input, where the key is making and breaking contact, the input clear may oscillate several times, may go from grounded to floating several times, but the output CLR, that stays steady at high. On the other hand, here what we are doing is throwing the key back again to start. So start has now been grounded, clear is floating, but once again start gets grounded, but it doesn't stay grounded because of the bouncing of the key, which is a purely mechanical effect. Start may go high again, that is floating again, then come into contact with the ground again, go low, go high, go low several times. However, the first time this happens, that is the first time start goes low and clear goes high, that sets the output CLR to low and CLR bar to high. And after that, when both inputs go high, even when the switch is bouncing, that again is a memory state. So the output just remembers what it was. So CLR stays low, CLR bar stays high. So this bouncing that you had at your key level, that is apparent in the start and the clear values, has been avoided completely in the output CLR and CLR bar. So when you want to actually control a digital circuit using the start and clear signals, you don't apply them directly to your circuit. You apply them after you send them through the switch debouncer, which gets rid of the mechanical problem of a switch making and breaking contact several times. So this is one very important application. Not necessarily the most important application of the Rs latch, but one important application where you get to use the Rs latch directly. Now the Rs latch is the basic building block of the flip-flops that are used in digital circuits. However, it is very rarely true that a bare Rs latch is used in a circuit. It is usually used more as a starting point from which you can build up more practical flip-flops. At the very least, you would have to clock a flip-flop in order to use it properly in a computer. The reason behind that is simple. A digital computer usually consists of thousands of such flip-flops, and it is important that they act in a coordinated manner. And in order to coordinate the behavior of these flip-flops, you essentially use a square wave input. This is called the clock signal. What this signal does is that it prevents the flip-flops from changing the output state at random times, allows them to change the output only at certain fixed intervals of time so that these changes occur together. Now, the simplest possible flip-flop with a clock would be a clocked RS flip-flop. Here I am showing you a circuit of a clocked Rs latch which uses NAND gates for its implementation. Notice that this thing here is our original Rs latch. But note that the inputs to this particular latch has been labeled R prime and S prime and not R and S. However, the theory is exactly the same as before, which I have summarized in this table on this side. Note that here, when R prime and S prime are both 1, that is the resting or the memory state, the output Q and Q bar does not change. Under such a condition, R prime equal to 0, S prime equal to 1 sets Q to 1. R prime equal to 1, S prime equal to 0 sets Q to 0. And both input 0 at the same time, that is the race condition. Remember, that makes both outputs go high, but then when the inputs go back to their resting state, the output is indeterminate. It depends on which of the gates is faster and so on. And that, as we have already said, is something we would want to avoid. But now, let us look at what the clock signal does. The clock signal here is written by this abbreviation CLK, and this clock signal is given to both of these two NAND gates. Also note one thing, the S and the R, the set and R reset for the whole circuit has been flipped a bit because it's the S which is above here and R which is below, and S feeds the NAND gate whose output actually is R prime, R feeds the NAND gate whose output is S prime. The reason for that should be very clear from the action of the NAND gate itself. Note that when the clock is low, when CLK is 0, then one input each of these two NAND gates is low and the output of the two NAND gates is definitely high. As a result, R prime and S prime are both high when clock is low, and therefore you are in the memory state. In other words, Q and Q bar will not change as long as clock is low, no matter what you do to S or R. Now, when the clock goes high, then of course the output of the NAND gate simply becomes the complement of the other input. That is, here R prime becomes S bar and S prime becomes R bar. So if S is 1, R is 0, then S prime, which is complement of R, becomes 1 and R prime becomes 0. Of course, assuming the clock is high at that moment, and that sets the latch. Q becomes 1, Q bar becomes 0. On the other hand, if when the clock went high, S were low and R were high, then R prime would be high and S prime would be low. The NAND latch here would reset and Q will go low, Q bar will go high. So whether the NAND latch is set or reset depends not only on what the values of S and R are, it depends also on whether the clock is high at that time. As long as the clock is low, the circuit simply does not respond to any change in the other inputs. This is how the clock coordinates the changes in the outputs of different flip-flops. Each of them are fed with the same clock signal, so each of them change their outputs at the very same time. What about the race condition? Clocking an Rs latch does not really avoid the race condition, but remember, here the race condition is actually obtained when R prime and S prime are both low. That can happen if S and R are both high when the clock goes high. In order to avoid race condition in a clocked RS latch, you have to ensure that the two inputs S and R and the clock do not go high at the same time. There are various clever ways of trying to achieve that, and we will meet some of them in a while. We can summarize the behavior of this clocked NAND latch in this table out here. Note that as long as the clock is low, it does not matter what R and S are, as we have said, the output stays in the no change condition. That is, whatever the output was before, it's held at that value. When the clock goes high, even then if R and S are both low, it's still in the no change condition. Only when the clock is high and you have R equal to 0, S equal to 1, that is, you are trying to set the latch gets set. When the input is high, clock is high, and you have R equal to 1, S equal to 0, the clock gets reset, the latch gets reset, you get a 0, and you get a race condition when all three inputs are high. Let me stress this line of the table just to remind you that because of the fact that each input, the S and R here, are actually going to two NAND gates before they reach the Q, what you have here is a behavior which is not really like the NAND latch. In the NAND latch, S and R both 1 is the memory condition, both 0 is the race. But in the clocked NAND latch, with clock high, S and R both 0 is actually the no change or memory condition. And with the clock high, S and R both high is the race condition. That is one thing you have to remember. That this is opposite of what happens in a single NAND latch as far as the memory versus race behavior is concerned. The same kind of behavior can be seen in this graphical representation here in what is called a timing diagram. Now, in most textbooks, you don't have this horizontal axis labeled, but it's really the time axis. It clearly shows how the signals change as time is flowing. The clock here is a square wave which goes high and low at regular intervals. And let's consider a situation where R and S are both low to begin with, and they stay low for quite a while. Now, as long as R and S are both low, you are in this line of the table or this line. Of course, if the clock is low, then you are in the no change condition anyway. But even when the clock goes high, you are in the no change condition, so the output does not change. We are just assuming that the output Q is low to begin with. So as long as R and S are both low, Q stays low. At this stage, S has gone high. So it might appear that the system should set Q, but it doesn't happen that way. Because note that S has gone high when actually the clock is low. And as long as the clock is low, there will be no change whatsoever. But now, with S staying high, when the clock goes high, Q now sets. So you have got a high Q. And this high Q continues afterwards, because note that here, of course, you are setting it so Q goes high. But after that, S has returned back to its natural value of 0, which means that no matter what happens to the clock, you are in the no change condition. In fact, you are in the no change condition even here, where R has gone high because the clock is still low. It's only when the clock goes high next that the latch will be reset and Q will return to 0. You should make sure that you understand the timing diagram properly, because this essentially holds the basic idea of how latches work in a digital computer. As we have mentioned over and over again, the race condition is what we want to avoid. Now, one of the ways to modify a latch and ensure that the race condition never occurs is to ensure that two inputs R and S will never be the same at the same time. This is achieved in what is called a D latch. Now, the D latch proper is what you see on the left, the circuit in black. Here, note that you have the standard Rs Nand latch, but is being fed with a single input, D. D is inverted before being fed to R, and D is not inverted and directly fed to S. So this actually ensures that depending on what D is, R will either be 1 and S will be 0, or R will be 0, S will be 1. In fact, S is always D, R is always D bar. So they are never equal at the same time. So the race condition definitely is avoided. But making the two inputs opposite to each other also actually robs you of the no change or memory condition. Indeed, the D latch on its own would have been a rather uninteresting circuit. As you can easily see, when D is low, D bar is high. As a result, R goes high, S goes low, and this circuit is reset. Q goes to 0. On the other hand, whenever D is high, R goes low, S goes high, the circuit is set. As a result, Q goes to 1. So, the upshot of all this is, in a D latch, Q is always the same as D, and Q bar is always the same as D bar. So, there seems to be no effect of a sequential circuit here. The feedback of Q and Q bar to the two intermediate NAND gates doesn't really have any effect. And frankly, it looks like this circuit does nothing whatsoever. You could have achieved the same thing just by using a simple wire joining D and Q and a NOT gate between D and Q bar. What makes a D latch actually useful is that you can clock it, and the clocked version is what we are going to discuss next. In the clocked version, you also can have this basic building block of the Rs Nand latch, and you precede that with a section which takes the clock in. Now, when the clock is low, both NAND gates here have one input which is low, so they produce inputs which are high. And remember, for the basic NAND latch, both inputs high is a memory state, so there will be no change. Note that when the clock is low, it doesn't matter what D is, there will be no change. So we have written down this table again, but this table here is slightly abbreviated. Instead of saying clock 0 D0, clock 0 D1, what we have done is written clock 0 and put an X here for D. X stands for don't care. So we don't really care what D is when clock is low. The output Q will simply not change. When the clock is high, D actually gets reflected in Q. So that is how the clocked D latch works. Now, the kind of clocking that we have talked about here is called level clocking. As long as the clock level is low, the output simply cannot change. On the other hand, the outputs can change when the clock level is high. Now that actually means that the outputs have a chance to change over exactly half of the duty cycle of the square wave input that you're giving to the clock. That is not really very suitable when you're trying to coordinate together the action of many flip-flops. Some flip-flops may change their output at the beginning of the duty cycle, some may change at the middle of the time when the clock level is high. Indeed, there will be quite a chaotic scenario. In order to prevent that, almost all digital computers use what is called edge triggering. Now I'm going to describe to you how to edge trigger a D latch using a very simple idea. This is a circuit diagram for the edge triggered D flip-flop. Notice that almost everything in this circuit is exactly identical to the clocked D flip-flop that we had just seen. The only difference is this. The clock signal, the square wave, is not directly fed to your D flip-flop. It's actually fed to the D flip-flop through a CR circuit. And what we do in this design is we deliberately keep the time constant of this CR combination very, very low, much, much smaller than the time during which the clock signal goes high. Now, what does that do? Let us just forget about the rest of the circuit for the time being, and let's just focus on what happens to the CR circuit when you feed it a square wave input. Now, if the capacitor is initially discharged, there is no potential difference between the two ends. And then if the clock signal goes high, this end of the capacitor goes up in voltage. But since no charge has got the time to flow yet, the capacitor has not become charged, so the potential difference between the two plates of the capacitor is still zero. So if this end goes high, the other end goes high at the same time. So that is what happens to this side. Then of course this capacitor discharges through this resistance very, very rapidly and returns to zero voltage almost instantaneously. So this is this sharp drop. When the trailing edge of the square wave, the falling edge, comes in, note that the capacitor voltage is almost back to zero by that time. The voltage, stored voltage between the two plates of the capacitor is back to zero. So is the voltage at this end because the capacitor is almost completely discharged. Now when the falling edge hits, this end goes down in voltage. So the other end has to go down in voltage too at the same time. And then you have a sharp comeback to 0 volts from a negative voltage. What really interests us is this: the leading edge of the clock leads to a sharp spike where the voltage at this end is high for a very short period of time and then drops almost to zero. And it is this which is fed to the clock signal of the D flip-flop. What that means is that the clock that the D flip-flop sees stays high only at the leading edge of the actual clock signal and only for a very, very short period of time. In the trailing edge, of course, the clock signal goes negative as far as D flip-flop is concerned, essentially is low. So what will happen is here, despite the fact that the actual clock signal is a square wave and which stays high for quite a long time, the signal which the circuit actually gets is very sharply spiked, and only during the leading edge of the clock signal will the output get a chance to change. So that has been illustrated in this timing diagram here. So here we have shown a square wave clock signal which goes up and down and stays up for quite some time, down for quite some time. But once it goes to the CR, this is what the D flip-flop actually sees. Sharp spikes, positive spikes whenever the clock signal goes up, sharp negative spikes whenever the clock signal goes down, but the negative spikes, just like the zero voltages, are treated as low by the circuit. So if you change the input of your D signal in this particular manner, this is just an arbitrary change that we have tried to illustrate. Note what will happen. Here the D has gone up. Remember, D and Q follow each other. Q becomes the same as D as long as clock is high. Now here, D is low and Q stays low throughout. D has gone high here. The actual clock signal is high, but what the D circuit is getting is zero. As a result, Q doesn't change, does not respond to D, it stays zero. It's only when you have this positive spike has come in because of the leading edge of the clock signal, and at that time D is high. Here on this positive clock edge, Q goes high, and then it stays high despite whatever D is doing because the effective clock to the circuit is low throughout. It's only when another positive edge comes in and you get a spike which is fed to the D, then Q responds to the D value, which is low, and goes back to low. So this is essentially how edge triggering is supposed to work. One important point though, in an actual practical circuit, you do not really use a CR to shape the clock pulse into these spikes. The reason you don't is rather simple. It's just economics. To create a capacitor on an integrated chip requires a large area. And in that area, you could have fit in perhaps thousands of transistors. So, whereas a capacitor is a pretty cheap discrete component, on an IC, a capacitor is very, very expensive. And you want to avoid it as much as possible. What are actually used in integrated circuits are much more complicated circuit combinations which effectively give you the same result of edge triggering, but without using an actual capacitor. Now those techniques are way too advanced for us to discuss here, but the upshot of this is straightforward. In an edge-triggered D flip-flop, the output will respond and change with the input. Q will become the same as D only on the positive or rising edges of the clock and not otherwise. Most practical flip-flops which are used in digital computer circuits have one additional modification. That modification is what is being shown here. If you look at this circuit closely, you will find that this is almost identical to the edge-triggered D flip-flop that we had drawn a while ago, except for these two AND gates which are sitting in the middle of the clocking part of the circuit and the original Rs latch. Now, one input of these AND gates each come from the clocking part of the circuit. The other inputs are marked PR and CLR for preset and clear. Now let us try to understand what these signals actually do. And also let me point out that in these applications, PR and CLR are inactive when they are high. So they are naturally kept high, and when you want them to act on the circuit, you send them to low and then take them back to high. That's the basic idea. Of course, when the input PR or the input CLR to the respective AND gate is high, then that particular input has no action. It's the other input which essentially determines what the output to the AND gate will be, and then it decides what will be fed to the Nand latch. So as long as PR and CLR are high, this circuit behaves exactly the same way as a previous circuit did. So what exactly does PR and CLR do? Note that when a computer starts up, all of its 1000 flip-flops essentially start up in some kind of random states. That's basically because of inherent fluctuations inside the circuit and transient effects. Now, in order to really start operations, there should be a way of setting some of these flip-flops to the desired high level and some other of the flip-flops to a desired low level. Irrespective of what the D signal or the clock signal is doing, at some instant of time you have to start with a definite state. Now note that if PR is driven low and then taken back high, the moment PR is driven low, the AND gate output goes low, and that forces Q to be high and Q bar to be low. So that is, it presets the D flip-flop to a high state. On the other hand, if you send CR momentarily low and then take it back high again, the moment CR goes low, the lower AND gate has an output which goes low, forcing Q bar to go high and Q to go low. So this way what we can do is we can override whatever D or C clock is doing. You can force the system or preset the system to high or clear the system so that Q goes to low. In this circuit, PR and CLR has priority. If you activate them, that is, send them low momentarily and then of course send them back high, Q and Q bar will respond. And after that, with PR and CLR going back to high, the normal operation of the flip-flop as dictated by D and the clock value can go forward. So this essentially is what the edge-triggered D flip-flop with preset and clear actually is, and this is close to the actual circuit that is used in digital computers. I say close simply because, as you remember, you don't really use a CR circuit to provide the edge triggering in an integrated circuit scenario. Since the D flip-flop is used often in a computer circuit, it deserves a symbol of its own. And the symbol is pretty straightforward. It's just a square block with the various relevant inputs and outputs marked. So the D input is marked, as you can see here. The clock input is marked, but note that this triangle edge present here in the symbol indicates that this is actually edge triggered. So the circuit is going to respond to the clock only in the rising edge. Q and Q bar, of course, are the two outputs which have been labeled here. And the preset and clear has also been labeled. These are the two inputs which override everything else. The bubbles on front of these inputs indicate that they are active low. That is, PR and CLR are kept high normally. When you send them to low, do they actually act on the circuit? When they are high, they don't have any effect on the circuit. So this is essentially what the basic circuit diagram symbol for this edge-triggered D flip-flop with preset and clear looks like. In many situations when we draw these things in a diagram, we may not indicate all the inputs. For example, we often omit the PR and the CLR input from the drawing simply so that the thing stays less cluttered. That doesn't mean that those inputs are not there. It's just that for that particular application, maybe you're not using the PR and the CLR inputs, and so you don't really bother showing them. Now, you might be wondering why we are spending so much time over this D flip-flop, which even with the clocking seems to do relatively little. When the clock is low, the output stays unchanged. When the clock is high or the leading edge comes in, the output simply follows the input. So what's so special about this? It may come as a bit of a surprise that even this very simple circuit is a building block of many very important pieces of a computer. Let us now turn to some of these practical applications. The first kind of practical application we are going to talk about is a buffer register. Now, a register is simply a group of memory elements that work together as a single unit. The simplest register does nothing more than just store a binary word. Well, others, like the shift register, modify the word that is stored by manipulating it in some way. Let me now first describe the simplest such register, just a basic buffer register, which you make using D flip-flops. So here, we have a buffer register which can store a nibble or 4 bits. Of course, you can extend this idea to store a byte or even more. Here, because we are storing a nibble or 4 bits, we are actually using 4 D flip-flops. We are not indicating every one of the inputs here, but the important things are you have the input D, you have the clock, and you also have the output Q. Q bar we are not showing simply because Q bar is just the complement of Q. Now the input to the 4 D flip-flops are given from the 4 bits which make up our nibble. That is, our nibble is the binary number x3, x2, x1, x0. x0 goes to the 0th or the rightmost D flip-flop. x1 goes to the 1th and so on. Now the operation of this particular register is very, very simple. As long as the clock is low, nothing happens. But when the clock goes high, Remember, these are all edge triggered as shown by these triangular symbols here. The moment the clock goes high, D0, D1, D2, D3 respond to the corresponding input values, and the outputs Q0, Q1, Q2, Q3 become X0, X1, X2, X3 respectively. And then when the rising edge of the clock goes away, any change that happens in the input nibble in between simply doesn't affect the output. That's a memory condition. Q0, Q1, Q2, Q3 stays unchanged until the next rising clock edge, where again Q0, Q1, Q2, Q3 will respond to the input values. So this is our simplest way of storing a group of bits in a register. The one problem with the simple buffer register is the stored value Q0, Q1, Q2 and Q3 will respond to the inputs every time a rising clock edge comes in. Sometimes you may not want that. You may want the value stored in the register to respond to the inputs only when some controlling signal is given. Otherwise, you would want it to stay unchanged. That is what is achieved by a modification of the buffer register called the controlled buffer register. And this is the circuit for that. Now this circuit may look a lot more complicated than what we had drawn a while ago, but let me assure you it's essentially the same circuit with a very small modification. Well, several small modifications. One of them is that we have explicitly shown the clear input here. Actually, I should have perhaps drawn bubbles at each one of these inputs just to indicate that the clear is active low. If clear is high, then nothing happens. When clear suddenly goes low, then the clear signal is given to each and every one of these D flip-flops and the outputs of each one of them goes to 0. So at the very beginning, you may just send the clear signal and force the buffer register to store just 0. What happens after that depends, of course, on this particular new additional thing that we have put in here. Now, it really is rather simple, and it becomes easier if you realize that all of the 4 D flip-flops here have been modified in exactly the same way. So if you understand any one of them, let's say this one, the leftmost one in your picture, you would understand what goes on in every one of them. So what has happened here is that instead of directly feeding X3 to D3, you actually send X3 through an AND gate. X3 becomes one input of the AND gate. The output of that goes through an OR gate and the resulting output goes to D3. What else does the OR gate get? The OR gate gets the output from another AND gate, which essentially has Q3, the output of this flip-flop, as its input. Now, the star of the show here is this signal called load. Now, this load signal is usually low, which what that means is this particular AND gate actually is inactive. Remember, if one input of a AND gate is low, then the output is automatically low. So it doesn't matter what X3 is. So as long as load is low, this AND gate will produce a low. The OR gate will not respond to that. The OR gate will respond to whatever it gets from the other one. Remember, the other one is coming through another AND gate, but that is connected to load bar, the complement of load, which is high. So this AND gate essentially passes Q3 into its output. The OR gate gets Q3 and low, so produces Q3. So here, as long as this load input is low, what happens is that the output Q3 of the flip-flop goes back to the input, and hence, irrespective of whether the clock is high or low, or whether the clock has just arrived or not, the output actually stays the same. It just sustains itself, and that happens in each and every one of these flip-flops. What happens when load goes high is load bar goes low. That means the output to the left end AND gate goes low, essentially contributes nothing. On the other hand, this right AND gate has x3 and high as input, so its output is x3. The OR gate's output is x3, which goes to D3. And so D3 now responds to the input x3 and changes Q3 to x3 when the next positive clock edge arrives. So to summarize, CLR can be used to set the register to 0000 at any given instant of time just by making it go low. The load signal essentially dictates whether the circuit is actually respond to the external inputs, and as long as the load signal is low, the circuit does not respond to x0, x1, x2, x3 at all. It just maintains whatever value it has. So this is how a memory device would actually work. Keep its output as long as the load signal is low, and when the load signal goes high, the input bits x0, x1, x2, x3 are loaded into the register. The next register that we talk about is a shift register. Now a shift register does not merely store an input set of bits, it actually shifts the bits to the left or to the right depending on what kind of register it is. And this kind of shifting operation is essential for many arithmetic and logic manipulations that are carried out in digital computers. Just to give you an example, if you just wrote down a binary number and shifted every one of the bits to the left, adding a 0 at the end, you're essentially multiplying by 2. So multiplication by powers of 2 can be done very easily by a shift left register. That's just one place where you could use such a thing. How is a shift left register constructed? The answer is very, very simple. The circuit that you can see here on your screen looks very much like the buffer register, with one important difference. There is only a single input to this circuit which has been labeled D-in here, and each output is fed to the next input. So Q0 feeds into D1, Q1 feeds into D2, Q2 feeds into D3, and so on. And of course, you have the clock, which is edge triggered as always. So let us try to understand how this circuit is going to behave. So let's assume that initially you have cleared all the outputs just by driving the clear signal to low, to its active value. We have not indicated that in this diagram, but you always do that at the beginning. So Q0, Q1, Q2, Q3 are 0 to begin with. And now you have a clock coming in, which once again, remember, is active only on the positive edges. And D-in is a signal which is just, for example, high until this time and then goes low. Now let us see what will happen to the various outputs and inputs. Now D-in is of course the same as D0. So D0, the input to the rightmost D flip-flop, is high to begin with, then goes low. Now when the first clock edge arrives after you have set everything to 0, Q0 jumps up to match D0. And then clock edges keep on coming and going. But since D-in stays high, Q0 simply doesn't respond. Now that D-in has gone low here, Q0, the output, does not respond immediately because remember here the clock is low. You might say that clock is high here, but remember this is not level triggered, this is edge triggered. So the response will only occur at the positive clock edge. So the positive clock edge is already gone. The circuit is going to respond in the next positive clock edge, which is now. So now the output Q0 responds to the input D0 and goes low. So this is how this one will behave. But what about Q1? Well, remember that Q0, the output of the rightmost D flip-flop, is also the input to the next D flip-flop, that is D1. Now, although I have shown Q0 to go high the moment the clock edge appears, because D0 is high, strictly speaking, there will be a slight delay because there will be some time needed for the signal to propagate through your D flip-flop. What that really means is that by the time this Q0 has gone high, the clock edge has already gone away. Which is why Q1, the output to the next D flip-flop, will not respond at that moment. It will stay low. It will go high only when the next clock edge arrives. And the same occurs on this side. This response Q0 actually does not occur exactly at this clock edge. It takes some amount of time to occur. So strictly speaking, this Q0 and hence D1 going low occurs slightly after this positive clock edge has gone away, which is why Q1 does not respond then. It responds only at the next positive clock edge. So you notice that whatever waveform you are getting at Q0, Q1's waveform is shifted in time. The same occurs for Q2 and Q3, and each case Q2 responds to D2 but only at the next clock edge. Q3 responds to D3 but only when the next clock edge comes along. So this signal keeps on shifting. That is what the shift register really does. The final circuit that we are going to talk about today is a controlled shift register. This is very much like the controlled buffer register. In fact, it's nearly identical to that. So I will not bother explaining its action all over again. All I will point out is that instead of the right end AND gate being fed x0, x1, x2, x3 as before, is actually being fed from the output of the previous one. So when this input, which is now called SHL for shift left, is low, this AND gate is out of action. It's this AND gate whose output comes through. In fact, Q3 is fed back to the input, Q2 is fed back to the input here, Q1 is fed back to the input here, and so on. And so Q0, Q1, Q2, Q3 keep on maintaining their values. On the other hand, when this input marked SHL for shift left goes high, that renders the left end AND gate in each of these controlled D flip-flops inactive. So Q3 is cut off from D3. It's actually Q2 which comes in via this AND gate. Remember, the other input to this AND gate is SHL, which is high. So Q2 comes in, goes to the OR gate, goes into D3. So the behavior that we get when the previous output is fed into the next input, as in the shift left register, that occurs now. So when SHL is low, the circuit essentially behaves like a register. It just keeps on storing whatever output it has. And when the SHL goes high, it shifts that output to the left. Now these are some of the basic building blocks of a digital computer. And you put these together along with some other very important circuits to build the computers which run our world nowadays. Other than the registers, there's another major kind of sequential digital circuit which is very, very important in building a digital computer, and that's called a counter. In fact, there are many different kinds of counters. We will meet the JK flip-flop, the one kind of flip-flop which we have not discussed yet, and its major applications in building various counters in the next lecture.